All right, so let's start this video with just the textbook definition of energy. Energy is the capacity of a physical system to do work. But that, of course, begs the question, well, what is work? And work is defined as the change in energy of a physical system. So we have a problem. This is a very cyclical definition here, right? It turns out that energy is just a really hard thing to define. What energy is really just a model that's useful for explaining why things happen and understanding why they happen and making predictions. But it's really hard to pin it down. A few things we need to know about energy is that energy and also work are scalars. So that means they have no direction to them, right? A vector would have a direction, but a scalar has no direction. To make a little more sense of energy, let's just look at a few different types of energy that are out there. So you may have heard of gravitational potential energy before. We're going to deal with gravitational potential energy in this unit quite a bit. That's the energy that you have from being above the ground. So if you have, I don't know, say a giant fridge and it's just 1 centimeter above the ground, you wouldn't be too worried about that, right? But if you lifted that giant fridge up to be like 2 stories above the ground, well, then suddenly you'd be a little bit worried, right? Because if that fridge fell, it could really do a lot of damage. And in fact, it could do a lot of work. So gravitational potential energy is energy that you have based on how high you are above the ground. That's one type. There's also kinetic energy you may have heard of. That's an energy that's based on how fast you're moving. So if you throw a baseball with some velocity, you throw it really fast, it's going to have more kinetic energy. One thing to notice here, right, it doesn't depend on direction. So this is true of all forms of energy. It doesn't depend on the direction of your velocity. So if you throw that baseball really fast straight up, or you throw it really fast at some angle, or you throw it really fast down, it'll still have the same kinetic energy. The kinetic energy is just depending on how fast it's going, not what direction that velocity is actually in. There's also thermal energy. Thermal energy is an energy based on how hot things are. It's actually really related to your kinetic energy. Kinetic energy is the energy of moving things. If you look down at the molecular level of, say, a cup of coffee, which I have beside me here, all the little molecules in there are moving at some speed. They all have some kinetic energy. That kinetic energy gives the cup of coffee a thermal energy or a temperature. There's many other types of energy as well that we won't get into too much. There's like nuclear energy. In your biology classes, you may have heard of chemical energy, right? There's ATP is that cool molecule that sort of stores energy for you in your cells. There's all those kinds of energies that are also very cool. We're going to focus on gravitational, kinetic, and thermal energy in this unit here, but you'll get into many more interesting types of energy. There's also electrical energy. Electrical energy. As you take more physics courses and chemistry courses and biology courses too. All right, so you've probably heard of the law of conservation of energy. That is the idea that energy can't be created or destroyed. So you can't just sort of come up with energy from nothing, and you can't get rid of energy once you have it. All you can do is take energy from one form to another. So if you have a kid at the top of a slide, they have some gravitational potential energy, right? They're high up above the ground. And that energy somehow turns into kinetic energy. They start moving down the slide. Well, how does that happen? That's through a process of work. And so that's what this video is about. It's the idea of work, which is how we transfer energy from one form to another. There's a formula for work that's kind of a new formula. You haven't really seen anything like it before. It's a force dotted with a displacement. So that's not a multiplication symbol, that's a dot product. You're going to learn all about dot product in calculus and vectors next year, which I hope you take. It's a really great course. But for now, what we need to know is a few interesting things about this formula. So first, force is a vector, right? And you know displacement is also a vector. When you dot two vectors together, though, what you get out is actually a scalar thing, something that has no direction. So force has a direction to it, displacement has a direction, and the direction really matters there. But when you dot them together, you get something that's just a number, no direction at all. So that's the first kind of interesting thing with dot product. The next is that dot product is related to multiplication, but it's not the same thing. What a dot product actually means is take the component of your force vector, which is parallel to delta D. So those two vertical lines mean parallel. Then you're looking for just the component of force which is parallel to your displacement, and then multiply that by all of your displacement. So to kind of draw that out, let's say you had a force vector like this, and a displacement like this. What you're going to do is split that force vector into components, and one component has to be parallel to your delta D, so it has to look like that. That's F parallel. There's also a component of F that's perpendicular to delta D too, right? We're not actually going to need that one, but there it is. And to calculate the work done, what you'll be doing is taking the entire component that's parallel to delta D and multiplying by all of delta D. That's what this formula here is. By the way, there's also another way you can do a dot product. If you have a force like this and a delta D like this, it's actually just as legit to split delta D into components. So you could split your delta D into one component that's parallel to the force and another component that's perpendicular to the force there. So this is delta D parallel here. And then we would take the parallel component of delta D and multiply by all of the force, and you'll actually get exactly the same number. So another way you could write this formula for work is that it's all of the force times just the parallel component of delta D. But most of the time I find it's more practical to split the force up and into components and take the parallel component of the force. So that's usually the way we actually do it in real life. All right, so work has units to it. The units are joules, which is the same unit as energy. So same as energy. But you might also see work as being Newton meters. If you remember, work is a force dotted with a displacement. Force has units of newtons. Displacement has units of meters. So sometimes people will write work in units of newtons times meters, and that's also fine. So either of these are good units for work. The symbol for work is capital W. And then what we do is we have a subscript afterwards that indicates which kind of force is doing the work. So you'll have a subscript that indicates the work done by a specific force. So say you have work done by a tension force, then I would call this like WT, the T standing for tension, or work done by gravity would be WG, work done by gravity. All right, first let's do a work done by a tension force. So here's a box being pulled forward with a tension force of 10 newtons over a delta D of 30 meters. So in general, your work is going to be by tension. It's going to be the force of tension that's parallel to delta D times delta D. So we get to look at this picture and say, well, what part of that tension force is actually parallel to delta D? Well, it turns out it's all of it. So that makes this question a lot easier. I get to take the entire 10 newtons because all of those 10 newtons is parallel to the displacement and multiply it by the 30 meters, which gives me 300 joules is one unit for work, or Newton meters. Just to round off to sig figs, looks like I've got 2 here, so 3.0 times 10 to the 2 joules would be good. Right, now here, same idea, but now the tension force we've got at an angle. So if the tension force is at an angle of 17 degrees, the first thing you need to do is to split it into two components. One of your components needs to be parallel to delta D. So that right there is FT parallel. It happens to be the X component, but it doesn't have to be. If your displacement had been vertical, then the component that's parallel would be the vertical component, right? So it all depends on where your displacement is, which component is parallel. You're looking for what's going to line up with delta D, and that one is parallel there. And there's a Y component too. We actually don't even need that one. The first thing you want to do is actually calculate FT parallel. You just use SOHCAHTOA for that. So that's going to be the total FT times cos of 17. It's cos because cos is close, right? So 10 cos 17 gives me 9.56 newtons there. And now I can calculate the work done by tension. So the work done by tension will be FT parallel times delta D. So I can actually plug in FT parallel, what I just solved for there, the 9.56, multiply by the delta D of 30, and I get 287, and the units will be either joules or Newton meters. And it looks like 3 sig figs looks fine from this question. So I only have 2 drawn in my picture, but I've got 3 here, so it looks like it's fine. So 287 joules would be my work done by tension. What about friction? So I've done kind of the work for you here and actually calculated the friction force. You could use your free body diagram and summing up the forces to figure out the friction force. And you'd also have to use the equation for FFK is mu k times Fn, but I've already done that work for you. So the friction force is negative 5.5 newtons. We want to know the work done by that kinetic friction force, which would be the kinetic friction force, but just the component that's parallel to delta D times delta D itself. Here, signs actually do matter. So work doesn't have any direction to it. You're not going to say it's some number of joules of work up, but work does have a sign. So when I have a negative force and a positive displacement, or anytime my force is pulling against my displacement, you actually want to put in a negative value here. So this would be negative 5.5 times the 30 meters there. So negative 5.5 times 30 is negative 165 joules. Let's think about what that means. So if you see a negative work done, that's a force that's pulling against where you're trying to go, then that means that you're actually removing energy from the system. So this sled or box, I guess it's a box, this box that's being pulled along is actually losing 165 joules of energy to friction, and that's just being released into probably heat in the environment, but it's actually losing energy here, whereas the tension force was giving the box some energy. That's a positive work, so that means the box is gaining energy from the tension force, losing energy from the friction force. All right, well, let's just write a sort of quick summary of that. So negative work by a specific force happens whenever that force is acting against the direction that the object's actually moving. So, sorry, so if the object is moving forward, your force is backwards, that's going to be negative work. But if, let's say, the object is actually moving backwards, maybe delta D is backwards, and your force is also backwards, this would actually be positive work here. Right? So it's only negative work only happens when your force is fighting you, when your force is against delta D. A situation sort of like this, maybe if your force is up, but your delta D is down, this would be a negative work situation here because the force is fighting the direction you want to go. So that's negative work. And that's when you lose energy from your system. All right, let's look at the force of gravity next. So I've calculated the normal force and the force of gravity for you already here. We want to know the work done by the force of gravity. That's going to be the component of gravity which is parallel to delta D times all of delta D. Well, when we look at this picture, notice gravity is straight down, delta D is forward. There's actually no component of gravity which is parallel to delta D at all. So this would be 0 times 30, or 0 joules. What that means is that gravity is not adding any energy to this system or taking it away. As the box moves forward, it's not gaining any energy due to gravity or losing any. What about the normal force? So the work done by the normal force would be that normal force, the parallel component, times delta D. Once again, we're in a situation where the normal force is completely perpendicular to delta D, so it does 0 work here. Delta D is 30. It doesn't even matter what it is, right? There's 0 joules of work is being done in this context. So let's sum that up. Anytime you have a force that is perpendicular to the motion, the direction of motion, your delta D, that force does 0 work on the object. So if you have a force this way and a delta D like this, that's going to be a 0 work situation. So always watch out for that. Forces that are perpendicular to your direction of motion don't do any work. Okay, so that's how we find the work done by individual forces. But if you remember, In our forces unit, we always found the net force, right? We were always adding up all the forces. And in the forces unit, it was a lot of work. You had to split the forces in, that was a terrible pun, isn't it? In the forces unit, it took a lot of effort to find our net force. We had to split force into X and Y, right? We would do this X and Y stuff, and then we'd find the net force in X and the net force in Y. I have really great news for you for this unit. When you're finding net work, which we'll do in this unit, it's way easier because work is not a vector. So the reason why we had to do this whole tricky thing with splitting all the X components of all our forces, all the Y components of our forces, adding all of those up, and then doing that little triangle to get the net force. The reason why we had to do all of that work is because force is a vector. Work is not a vector. So when you're finding net work, you just get to add up all the works. You just literally add up the numbers, and that's all you do. So to find net work, you're going to start with a free body diagram just to see what your forces are, so you know all the forces that are on your object. You're going to look at each force individually. So just like we did for that box, we went through the tension force, the friction force, the normal force, the gravity force. We find out the work done by each force individually, and then you just add up the numbers, like just straight up add them. Don't use vectors. Don't try and find X and Y components of them. Just add the numbers straight up. The only thing to watch out for is the signs. So if you have negative signs, make sure you keep them negative. If you have positives, of course, keep them positive. But that's all you have to do. Okay, so here is the situation we've already been looking at. So we've already found all of these works, right? The work done by tension, that was the 10 newtons times cos of 17 times the displacement, which was 30. That was 287 joules. We found the work done by the friction force was a negative work because the friction force was opposing the direction of motion. It was removing energy from the system, and it was negative 165 joules. It's a 5, sorry. We found the work done by gravity was 0 because it was perpendicular to the delta D. We found the work done by the normal force was 0. And those were all the forces that were on the box. So when you want to find the net work, all you have to do is add those numbers up. There's no X and Y components here. You're just going to add up the work done by tension, the work done by friction, the work done by gravity. Oh, sorry. The work done by gravity and the work done, I keep wanting to write forces here. I'm a step ahead here. Work done by the normal force. So that net work, it's just going to be the 287 joules plus the negative 165 joules plus 0 for gravity's work and 0 for the work done by the normal force. So that gives us a net work of 122 joules or 122 Newton meters if you want to use Newton meters, and that's it.